Hi, my name is Ryan, and today I will be talking about my work on scalable and sustainable deep learning via randomized hashing. This is joint work done with my advisor, Dr. Anshumali Srivastava. So first, I will start off with a familiar example, object recognition and the ImageNet competition. This is the main example of how deep learning has become the de facto standard for many machine learning tasks. Going forward, neural networks will learn from many different domains, for example, fusing together image, text, and speech data into a single network. Now, this is obviously a natural evolution for neural networks. Everyone in the audience today is processing this presentation using multiple senses. You are reading the slides with your eyes and listening to me talk in order to gain a more comprehensive understanding of the information. The same principle will apply to neural networks. Multimodal learning will help improve their robustness and capability. Here's an example of this transition already taking place. This paper was recently posted on arXiv in July, and it was titled, "One Network to Rule Them All." Essentially, Google took several independent networks and merged them together into a single massive network, allowing it to tackle multiple tasks across many domains, i.e., it can handle object recognition, language translation, image captioning, and much more. Now, the challenge is that learning from all of that information will require us to build even larger neural networks. Simply put, neural networks will need larger parameter spaces in order to handle all of the information contained in large data sets. So here's evidence of that point. This paper was titled "Outrageously Large Neural Networks," and its goal was to improve the accuracy of large-scale language models. And so they added a mixture of experts layer containing billions of parameters to a language model. It is essentially a massive gated, fully connected layer. The key takeaway was that you could achieve better accuracy simply by increasing the model size. However, the computational challenge with building larger neural networks is that they require handling billions of floating point operations in the form of large matrix multiplications. Now, one potential solution is to use low-rank approximations. From the perspective of a neural network, a low-rank approximation is equivalent to adding an intermediate layer with R nodes. This converts the original weight matrix into two smaller low-rank matrices with rank R, thereby reducing the computational cost of the matrix multiplication. Now, the drawback with low-rank approximation is that it produces dense gradient updates, which are hard to parallelize. Another aspect of large-scale machine learning is to effectively utilize parallel computing. Data parallelism is a simple and successful way of using multiple processors. With dense gradient updates, their asynchronous updates can overlap with each other, causing poor convergence. In addition, transferring dense gradients can cause communication bottlenecks in distributed settings. Now, the concept of asynchronous stochastic gradient descent is simple. The model is duplicated several times, and the data is divided into several independent pieces. Each model replica processes a piece of the data concurrently. The gradients for each model are asynchronously transferred back to the parameter server. Now, the main benefit is that we can achieve linear speedup with respect to the number of model replicas. However, ASGD requires random, sparse gradients for the model to converge correctly. Suboptimal convergence is one of the main reasons why ASGD has fallen out of favor for training deep learning models. We plan to address this issue using our randomized hashing approach, which both reduces the computational cost of the neural network and is suitable for asynchronous training. Now I will describe the methodology behind our LSH deep learning framework. So the development of our randomized hashing approach starts with a familiar regularization technique, dropout. Now, dropout randomly disables a percentage of the neurons in the network, preventing dependencies between neurons and improving performance. Now, normally, only 50% of the neurons are disabled. The question we are interested in answering is this: can we disable an extremely high percentage of the neurons without causing the network to perform badly? Now, part of the answer to that question comes from an enhancement to vanilla dropout called adaptive dropout. The insight behind adaptive dropout is that there are groups of neurons that detect features in the network with high confidence. Instead of randomly disabling a portion of the neurons, we should only keep the expert neurons active and then disable all of the rest. So now I will walk you through a brief example of adaptive dropout using a toy network with a single hidden layer and 5 neurons. So the first step is to compute all of the activations for the neurons. Next, we flip a Bernoulli coin for each neuron whose probability of success is monotonic with respect to the neuron's activations. And so, we sample each neuron in proportion to the magnitude of its activation. Now, after sampling the neurons, we perform the regular forward and back propagation steps only on the sparse set of sampled neurons. So the good news is that we can find a sparse set of expert neurons. However, the bad news was we had to compute all of the activations first in order to do so. Therefore, this algorithm doesn't save any computation. Now the question becomes, can we intelligently identify the set of expert neurons without computing the activations first? So now this is where locality-sensitive hashing comes into the picture. Our solution is to use LSH to sample the expert neurons efficiently in near constant time. But first, what is locality-sensitive hashing? Well, a hash function maps a vector to an integer key. The locality-sensitive property means that the probability of 2 vectors hashing to the same key is proportional to some kind of similarity metric. Basically, similar items are more likely to collide together and have the same hash value. So let's look at another toy example. So say we have a group of colored balls, and we want to divide them into 3 buckets using an LSH hash function. Now here are some potential results. The mapping on the left is more likely to occur than the one on the right. The balls on the left side are neatly organized by their colors. On the right side, the gray ball is mistakenly placed in the bucket with the red and orange balls. With locality-sensitive hashing, this is an unlikely event. So now we're coming back to neural networks. Instead of placing colored balls into an LSH hash table, we will be inserting the neurons of the network. After all, they're only weight vectors. When executing the network, we use the LSH hash tables to sample the expert neurons. This sampling operation is very fast because hash tables support insertion and deletion operations in near constant time. Now I would like to take a moment to explain this algorithm from the perspective of another common deep learning technique, sample softmax. It is commonly used to train language models with large vocabularies where computing the full softmax layer is very expensive. So here's a reminder of why sample softmax works. The nice thing about words is that their distribution is static. It follows a power law distribution. And so we can sample a sparse set of words from a log uniform distribution and then use those words in order to approximate the cross-entropy loss. Unfortunately, this approach does not work for the hidden layers of the network. The distribution of neurons is dynamic. It is constantly changing based on the input. Luckily, we can sample the expert neurons from a dynamic LSH distribution instead of a fixed log uniform distribution. Therefore, you can view our approach as a version of sample Softmax, except it targets the hidden layers of the neural network. So to summarize, the LSH distribution allows us to sample the neurons with probability monotonic with respect to their activations. We believe this is the first sampling view of locality-sensitive hashing. If you're interested in learning more, you can explore how we build on this LSH sampling viewpoint in our paper on arXiv. So now I will show you an example illustrating how everything comes together in our LSH deep learning framework using another toy fully connected network. So the first step is that we pre-process the neural network by building hash tables from the hidden layer's weights. Each hidden layer has a unique set of hash tables and randomized hash functions. Now we move on to the execution phase of the network. So say we are given an input to a hidden layer. We apply the randomized hash function for that hidden layer to the input, which gives us that input's integer fingerprint. Next, we query the hash tables for the hidden layer using the integer fingerprint. The neurons retrieved from the hash table becomes our sparse active set. These neurons are sampled in proportion to their activations, just like adaptive dropout, and as explained earlier in the talk. Finally, we perform the forward and back propagation steps using only the nodes in the active set. Now the computational cost for the network is on the order of the active nodes. If you were performing this step on a GPU, on a practical system, you could use a gather operation to convert the sparse set of neurons into a small, dense weight matrix, allowing you to use the standard matrix multiplication operations you normally use in those packages. We maintain the hash tables by periodically updating them to account for changes caused by a gradient descent. So the neurons in the active set are rehashed and now have updated positions in the hash tables. This maintenance phase is efficient because we only have to update the neurons from the sparse active set. The rest of the neurons are left untouched. Now I would like to tie everything together and go back and highlight the key differences between low-rank approximations and our sparsity approach. Since the active set is sparse, only a few neurons are updated in the gradient descent step. Therefore, if you have multiple models running asynchronously, their gradient updates are unlikely to overlap with each other. In addition, since you have fewer gradients to transmit back to the parameter server, you have lower communication costs. So now we come to the experimental results of the paper. The first question we were interested in answering was, how sparse can we make the network without affecting its accuracy? So the first thing we learned was vanilla dropout fails at high sparsity levels. So each one of these plots is an experiment on a different data set. The x-axis represents the sparsity of the network, while the y-axis represents the network's test accuracy. Our randomized hashing approach is the blue line, and the purple line is vanilla dropout. So as you can see, there is a clear trend that as the level of sparsity increases, the accuracy drops for vanilla dropout. Now, there is an especially dramatic decrease in accuracy for vanilla dropout when the sparsity level reaches 5 to 10%. Now, this is important because we're interested in extreme levels of sparsity in order to save computation. On the other hand, our randomized hashing approach remains relatively stable as the sparsity level increases. We also compared our randomized hashing approach against the other expensive but exact approaches like adaptive dropout and winner-take-all, but those results were included in our paper. We didn't include it in our talk for time considerations. But now we move on to the next set of questions that deal with asynchronous stochastic gradient descent. We wanted to determine how the convergence of the network is affected by increasing the number of models running asynchronously, and how much the wall clock time decreases as we increase the number of models running. So these plots show the network's accuracy over a number of training epochs. The black line represents a standard neural network with dense gradient updates. The purple line is our randomized hashing approach with sparse gradients. Our approach outperforms or matches the standard network's conversion rate, which confirms that sparsity allows for faster, more stable convergence. And finally, we measured our performance of our approach on a workstation with 56 processors. And as expected with lock-free asynchronous gradient descent, it shows that our LSH approach achieves roughly linear speedup as the number of cores increases. We see diminishing returns depending on the size of the dataset, but if you have a large enough dataset, you would obviously see much better speedup. So the final upshot is that random, sparse gradients make machine learning models easy to scale using data parallelism. So in conclusion, the goal of this paper was to minimize the amount of computation necessary to train neural networks while exploiting data parallelism using asynchronous stochastic gradient descent. Our solution was to sample a sparse set of expert neurons using locality-sensitive hashing in near constant time. And finally, for our future work, we are currently in the process of implementing a general LSH framework for GPUs with API support for TensorFlow, PyTorch, MXNet, and whatever kind of deep learning framework comes out in the next 6 months. And then with that, we've reached the end of my presentation. Thank you.